Welcome, everybody. We are here with us today. My name is Erin Cameron, and I'm the Development and Outreach Coordinator for SACE. I'll be your facilitator for today's webinar, Understanding Concerns with Dry Sorbent Injection as a Coal Plant Pollution Control. On behalf of SACE, I'd like to thank you for attending today's webinar. Your interest and support are critical to the work that we do. We will be recording this webinar, so all lines have been muted to assure recording quality. I encourage you to type in your questions using the questions option on your control panel. We will then answer the questions in the order they're received at the very end of the presentation. I also want to add that all material from this presentation will be available on our website, cleanenergy.org. For those of you not familiar with SACE, we are a regional organization focused on promoting responsible energy choices that create global warming solutions and ensure clean, safe, and healthy communities throughout the Southeast. SACE has been a leading voice for energy policy to protect the quality of life in treasured places in the Southeast since 1985. We are a membership organization, and I'd like to thank all of our members on this call and encourage those of you who are not members to please join us today. I'd now like to turn the presentation over to Angela Garoni, SACE Southeast Energy Research Attorney. Angela.
Thanks, Erin. And I'd also like to thank all of you for taking the time to attend this webinar. We at SACE became aware of dry sorbent injection, DSI, as a sulfur dioxide pollution control when southeastern utilities began to propose it as a pollution control and compliance solution for the upcoming federal air regulations. The Southeast is home to a large number of older, uncontrolled plants, and we became concerned that DSI could provide a life extension for these coal plants that we believe ought to be retired rather than retrofitted. And as we began to dig deeper into DSI, we recognized that this is an issue of national significance and that there is a need for the larger environmental community to have a better understanding of this technology. So we hope that this webinar will provide each of you with a better understanding of this burgeoning technology and not only the design and implementation of DSI, but also the multitude of impacts of implementing DSI, both on air quality and water quality. Our presenter today will be Dr. Ron Sahu, an environmental energy consultant, who will present the technical background and concerns of DSI. Dr. Sahu has 23 years' experience as a consultant and expert witness, providing his expertise to private industry, government, and various public interest group clients. Prior to his consultant work, Dr. Sahu worked as a process and thermal design engineer and conducted his PhD work in coal combustion engineering. He has also served as an adjunct professor at various Southern California schools over the last 20 years. Thank you all again for joining us, and I'll now turn it over to Dr. Sahu to begin the presentation.
Thank you, Angela. Good morning or good afternoon to all of you. I'm going to walk through a slide deck here, and looking at the list of attendees, I can see a few familiar names, and hello to all of you, and for those of you that I don't know, good to meet you too. It's a little hard doing this without getting feedback like I'm used to in a live audience, so I will do my best to hit the highlights in every slide, the sort of key message that I'm trying to convey, and then as Erin mentioned, there will be time to hopefully take many questions, or as many questions as we can before the webinar ends, and you can always follow up later on with me directly with email or by phone for any follow-up questions. So a DSI stands for dry sorbent injection, and in this case, the dry truly means dry. There is you don't want any moisture as part of the injection process, and the sorbent, as we will see, could be one of several candidates. And the DSI technology that we are interested in today, and we're focusing on today, has to do with sulfur dioxide control, SO2 control. We'll see in a couple of slides that the technology first began about 10 years or even longer, or ago rather, as a control for other pollutants like acid gases, like HCl, and also for sulfur trioxide, SO3. And it later on has taken on a new lease of life as a SO2 control, and right now the most active implementation of DSI seems to be focused on SO2, and that is where we will focus our attention. The chart here shows a very simple cartoon or schematic of the typical DSI system. You have the bulk material, which is the sorbent itself, coming into the facility, and it's typically stored in the receiving silo or a storage silo, and then blown into a day or a more ongoing silo that is properly sized to contain about a day's worth of material for the boiler into which it would be injected. It goes through a feeder and a mill and a blower, and we'll talk a little bit about that detail in the next slide. And then, as we will discuss later, you could inject the sorbent at one of several locations. Typically, it is after the economizer, but it could be before the economizer, after the economizer, or after the air preheater, and before the particulate control device, which in this case is shown as a ESP or a bag filter or bag house before everything, the clean gases go up the stack. If we could have the next slide, please. So here we want to show a little more detail, mainly making the point that the injection system can be fairly sophisticated and would need to be fairly sophisticated depending on the sorbent that one is thinking of injecting. You might need air conditioning of some sort. I show an inlet dehumidifier, for example, to take care of the moisture that may be in the ambient air. And you have to properly account for not introducing too much moisture for reasons we'll discuss in a minute. You might need to control the temperature also of the injecting gas and the injectant gas before it goes into the actual point of injection. We'll get into some of these details as to why they're important in a little bit. If the next slide, please. And this is a summary chart that I wanted to highlight a few issues on. The title here is taken from an older presentation where this was geared, as I mentioned earlier, to SO3 removal, and that's why the slide shows SO3. But the type of sorbents that are highlighted here have historically been used for SO3 as well as for acid gases and also for SO2. The one we will focus on a lot is Trona, and it's a particular sodium-based sorbent that is naturally available in the United States. We also have had application of this technology using other types of injectants that are shown here, hydrated lime, and magnesium hydroxide, and others. At the very bottom, you will see a new term called typical NSR. And in this case, NSR stands for normalized stoichiometric ratio. And this is an important parameter. Very simply, it means how much sorbent you have to add in relation to the theoretical amount of sorbent that is necessary to deal with sulfur dioxide. I'll give you an example here. If you want to remove 1 pound of sulfur dioxide from the gas, and you're using Trona, you need about 2.4 pounds of Trona to theoretically remove the sulfur dioxide, assuming the chemical reactions are all complete and assuming you absolutely have perfect mixing and all of the reactions that you would like to occur. So you need about 2.4 pounds for each pound of sulfur dioxide. And that would correspond to a normalized stoichiometric ratio of 1. So if you want to get the higher efficiencies of sulfur dioxide removal, you cannot get that with simply adding the theoretical amount. You need to do more than that. You need to have excess sorbent. And so when you're talking about an NSR of 2 to 3 or 1 or 1.5 or some other multiple, it simply means that many times greater than the theoretical amount that I just mentioned. So the amount of sorbent that you need to inject is going to be a function of variables we'll discuss. But you'll see the term NSR, and I just wanted to spend a few minutes clarifying what that term really means in this context. We could go to the next slide. And here I wanted to show a historical slide. I mentioned that the technology, at least in historical terms, was required for or used for HCl. And I wanted to show this cross chart of HCl removal versus SO2 removal, because generally these technologies do better on acid gases and SO3 than they do on SO2. And what this chart shows is while you could get 60, 70, 80, 90, close to 100% or 99% or 98% removal of HCl, you have a harder time for the same amount of Trona getting those sorts of high levels of SO2 removal. So SO2 removal will lag for a number of reasons, including how the chemistry works, how the mixing works, how the contact time works, how the residence time works, and so on. Let's go to the next slide. I'm not going to spend much detail on a few slides like this, except to show that if you're thinking about the grand scheme of SO2 removal and you've already ruled out things like scrubbers, dry scrubbers or wet scrubbers, and you're into a serious consideration of dry sorbent injection, then there are some decision trees you have to navigate as to what type of sorbent, and later on we'll see how that sorbent should be processed. And for our purposes here, we are talking about SO2 removal applications now that exceed 50%, whether it is to meet EPA's MATS rule or whether it is to deal with reducing SO2 for other purposes like National Ambient Air Quality Standards and so on. So if you look at that, then the calcium-based injectants such as hydrated lime are not favored. Instead, you want sodium-based injectants like Trona or sodium bicarbonate. That was the SBS, by the way, in the previous table a few slides ago. And so we could go to the next slide now. So that's why I'm going to focus this presentation on Trona as an example. And that happens to be one of the more common type of sorbents that are under consideration for a number of reasons, including that it is cheaper than SBS. And we'll talk about cost a little bit later. We could go to the next slide. Erin, we could go after this slide 8. We could go to 9. Yeah, thank you. On Trona, the actual name is sodium sesquicarbonate, and you can see the chemical formula there. It's a combination of sodium carbonate and bicarbonate, and it's hydrated. It is a naturally occurring mineral, and in the U.S. we have large deposits. There's some in California, in actually a place near Trona, near Bakersfield, but the bulk of the deposit is in the Green River Basin in Wyoming, coincidentally not too far from the Powder River Basin where we get a lot of our low sulfur coal from. And it's a very, very large geologic formation that has known deposits exceeding 100 billion tons of Trona. And various companies, 4 in particular, are mining it. We could go to the next slide to get an idea of the location. This shows the sort of the southwestern corner of Wyoming, and you can see the other bordering states. And the bedded Trona is the little red, as you can see in the middle, and we can expand that in the next slide. I just wanted to give some background on Trona because it is so widely used right now. On the next slide, you'll see the actual mining areas and so on for the different companies. And the two that are most active in supplying dry sorbent injection to companies are Solvay and FMC. So you can see their Trona deposits or their mining areas. And then, of course, it's located in seams at different depths in the ground. We get an idea of that in the next slide. And there are multiple layers, about 20 or 30 different layers, roughly speaking, some as thin as a few feet to about 10 to 12 feet thick. And the next slide shows a typical mining seam where Trona has actually been mined, and you can see a relative idea of a person standing there and the kind of mine configuration that the Trona is actually pulled out from. Now, this Trona, with very little processing other than maybe size reduction, can actually be injected to get the kind of effects we're talking about. We can move to the next slide. I don't want to spend a lot of time on the detailed chemistry except to note a few things. The sodium-based reactions are what are our focus right now. You have a parallel set of calcium reactions that I note here in case somebody selects hydrated lime or some of the other sorbents that I mentioned previously. But the sodium-based reactions, you're essentially doing the same thing. You're substituting your sulfate, if you will, or you're creating sulfates by displacing the carbonates in your injected sorbent. And so if you look to the right-hand side, you will see that what started out as a sodium carbonate or a sodium bicarbonate essentially ends up as a sodium sulfate, SO4. And one key thing to remember, and it is one of the byproducts, if you will, of this process, like it is of many other sorbent or desulfurization processes, is you will produce carbon dioxide gas. You can see CO2 as a product on the right-hand side in many cases. And so CO2 will be produced. And of course, when you inject the dry sorbent like Trona or SBS, or for that matter, some combination of the two, you will produce CO2. And that will be over and above the amount of CO2 that is normally produced in the combustion process if you're burning coal. We can go to the next slide. The Trona that is received, if you will, it is transported in rail from the Green River Basin, and typically in 100-ton rail cars, and they're transported to the point of application. You need to typically have a size that can be blown or injected into these various locations that I spoke about earlier. And the sizing affects the utilization of the reagent. In other words, the finer you grind the Trona particles that you would expect, you would get better utilization. And in some ways, you will lower that NSR ratio. That means you will need less excess quantity of the reagent than you would if you did not size it properly. So most Trona is sized or milled down to certain lower and smaller particle sizes at the plant site, because that improves the utilization, and therefore if you can use less of it, then of course it removes it reduces the waste and other things we'll talk about. But there is a cost to further milling it, and there is a trade-off. So we're talking about sizes that are in the, anywhere from 10, 15, 20, 25, 35 microns on average for the median size of the particles that are injected, and that can be then carried by this conditioned air into the exhaust gas stream. Next slide. Now I want to spend a few minutes talking about the location of injection in a little more detail. So your location in some ways depends on the temperature, and that temperature is again a function of the sorbent. If we are talking about Trona and sodium bicarbonate, or let's say Trona, then it is less effective, as you see, once the temperature falls below a certain threshold, in this case indicated roughly about 300 or 290 degrees Fahrenheit. And so you have to see that the point of injection should be at temperatures that are significantly greater than that temperature, because the reactivity, if you will, the chemical reactions are not going to be as effective, and you will simply not get that much utilization of the Trona that you're going to inject. So the temperature profile of the exhaust gases as they leave the boiler, as they leave the economizer and go to the air preheater and then move on to the bag house and so on, are important in deciding where to do the injection. And of course, you will have to do the injection before the particulate control device. You cannot do it after unless you have a secondary collector. But if you have one main particulate collection device, then it has to be after, because the Trona, the particles that have absorbed SO2 will have to be captured as part of the baghouse dust. And again, the popular locations are either the economizer outlet, which is the same thing as the air preheater inlet, or the after the air preheater outlet and before the particulate control device. In a few rare cases or less frequent cases, it is also injected before the economizer. Let's go to the next slide. And then this, I was talking about milling, or essentially size reduction. And you typically have a grinder or a pulverizer or a milling machine at the site where the received Trona is ground into the appropriate size and then put back into the day hopper or into the injector directly. And some of that is a function of how big the facility is, because the cost differential and the utilization economics does depend on how much. A rule of thumb is this 3,000 pounds an hour. It's a fairly significant injection rate, and it might, as it turns out, be more effective to do milling, to take on the investment of the capital costs of the milling machines and the operating costs for the milling, to justify the improved utilization, and therefore the lesser quantities you'd have to handle. But again, as I said, if you have a large installation, and by large I mean extremely large, those of you that saw the announcement a couple of weeks ago or a week ago about AEP's Rockport facility, that's a 2-unit facility with 1,300 megawatts at each unit. So they're extremely large installations, and that's probably the biggest that the DSI has been slated to be used, and we can talk more about that in Q&A. But you will almost certainly consider milling if you're going to use Trona. Next slide, please. What happens when you inject these Trona particles into the hot gas stream? What happens is they essentially bubble up. The surface area increases. They become, you get this popcorn effect. And that's what is shown here, is this increase in surface area as a function of temperature. And you want that surface area increase because that is what is helping provide the surface area for the SO2 to adsorb and then to react with for the chemistry to be effective. So this shows that to get effective maximum utilization, you really want to be in the 500 degrees, the 400 to 600 degrees temperature range, because anything below that, very low, you see the 100, 200, 300 degrees, the surface areas are not very high. And if you get to very, very high temperature on the other side, the Trona essentially sinters and it chemically transforms and you lose utilization. So there is a sort of sweet spot in the temperature window where you want the injection, and that is really what drives that injection decision, in addition to the practical considerations of collecting it before the bag house and so on. And therefore, I wanted to give you this to give you a better understanding of why the injection point is typically where it's at. We can go to the next slide. And now I'm going to talk about a little bit of at least available data on the type of reductions people are seeing. And this in one chart shows So2 reduction on the left, and you can see it goes, in this case, tops off at about 60% based on this data set. And you can see the economizer inlet, which is the blue diamonds. You can see the air heater, which is the red squares, and then the triangle, the green triangle, is the ESP inlet, which is really after the air preheater. And this shows that you really, of course, never inject at less than the stoichiometric ratio. So NSR is at least 1 or greater. Remember, 1 means you're pretty close to the theoretical limit. It is, by definition, the theoretical amount you need. And so 2 in this case would be twice. And you see most of the data points here are greater than 2. That means you're injecting at twice the theoretical utilization rate. And you can see a little bit more effectiveness at the economizer inlet because it's got longer residence time and factors like that. But the range is in the 30 to 55 or 60% removal. We will see that in specific installations and under specific conditions, you can get higher SO2 removals. In other words, 60% is not the maximum by any means, but it does take a lot of Trona, it does take a lot of sorbent, and we'll see that in subsequent slides. Let's go to the next one. And this is another set of trials, and this now we see that at the very high end, you can see at a NSR ratio of 3.5. That means that is 3.5 times the theoretical. So if you remember the 2.4 number I mentioned, that's the 2.4 pounds per every pound of SO2 removed, 3.5 times that, you can do the math, is 3.5 times 2.4. You're close to 10 pounds of Trona or thereabouts for every pound of SO2 that you're removing. And of course, you do that, and at the right injection point, you're now getting a reduction, at least in this set of trials, that is greater than 85 or close to 90% or greater than 95, I mean, in the mid 90%. But that is unusual. That is a lot of Trona, and it's a lot of material handling. But you see the sensitivity of the NSR ratio as well as the injection point and the injection strategy in terms of the removal efficiency. So you can have a wide range, and the operating parameters and the cost will really dictate what you can achieve. Now, you will never get the 98 or 99% efficiencies that you might get with a wet scrubber. It is difficult to get consistently a 95% like you might get with a dry scrubber, but you can certainly see that it's a matter of how much and how overwhelming you can do the injection in terms of getting the mixing with the SO2. Let's go to the next slide. I mentioned way back in the beginning that the air, the conditioning of the air is an important factor, and I show that in this slide from a vendor. Conditioning in this case means dehumidification as well as some degree of temperature control. And you can see, we can look at this chart a couple of different ways. What it shows is the non-conditioned air, just ambient air, is in blue, and then the conditioned air is in the red or the brown dots. So you can look at it both ways. Let's take for a given amount of expected SO2 reduction, let's say 60%, and you look across the chart, you can see that you get that same degree of SO2 reduction, but you get it at a lot lower NSR ratio. That means with less material if you have conditioned air than if you don't have conditioned air. The other way to look at it is, of course, for a given NSR, you can take, let's say, at 1.5 and almost kind of draw a vertical line. For a given NSR, for a given amount of material, you will get essentially different levels of SO2 reduction with conditioned and non-conditioned air. Now, you get better reduction with conditioned air, or for a given amount, or you get the same reduction for less with conditioned air. Either way you look at it, conditioning, again, helps. Of course, it is also an added cost because you have to dehumidify and you have to maybe keep the temperature properly. And we'll see conditioning has yet another effect that I'm hoping is on the very next slide. Let's go to that one. Yes, now this is taken from actual data, and it shows one other thing, which is these hydrates, basically these carbonates and bicarbonates, and these hydrates, if you don't condition air, they can actually pick up moisture from the ambient air, and they can start creating conveyance problems. They can actually block lines, and they can actually create, significant fouling in the equipment and in the handling system. So some amount of conditioning is essential just to make sure that your system doesn't plug up. What you see on this, to dramatically illustrate that, you see on the y-axis, on the vertical, is blower pressure. Imagine that there's a fan or a blower that is blowing this into the injection system. I mean, rather, that's blowing the Trona into the actual flue gases that are to be treated. And the higher blower pressure simply means you're reaching more resistance. You're basically encountering more fouling. And what this is showing is the effect. The runs A and B at the very left, ambient air, and with reasonable amount of carbon dioxide that is typically in the atmosphere. As 400 ppm is the typical atmospheric concentration of CO2. You can see very quickly, within a few days, just third day, the blower pressure starts to go really high. That means you're starting to get significant blocking. You reduce the CO2 value, part of your conditioning. You're dropping out the CO2 a little bit along with the moisture, and you see now that you're able to go much longer, maybe 10, 12, 14 days before your blower pressure rises up again. And then finally, you see that if you go to you have an air cooler and you have other more sophisticated conditioning, you pretty much stay at a low blower pressure for very long, in this case for a couple of months, without fouling problems. So the practical need, and I mention all this because it seems like a very simple installation that you just bring in some dust and you just blow it into an airstream, and voila, you have a reduction that you want. But in reality, the operating issues are fairly important and will drive a lot of decisions and have to be, paid close attention to if you want to get this technology working, and especially if you have to sustain a claim of a high efficiency over a long duration. Let's go to the next slide. Some more challenges. We were just talking about the plugging and caking issues that I just mentioned. They can dehydrate in the conveying system. That means now you're losing water, and that water then becomes available to agglomerate and further make this caking a worse problem. And then, so the way around that is you really have to minimize. You have to properly control temperature essentially, and the CO2 concentration and the moisture concentration in the entire stream. That's the key takeaway in terms of designing a handling system that will go for a long time without causing problems. Next slide. Some more important concerns that I think really need to be fleshed out with this technology is, first of all, I'm going to mention ash sales. Now, in many cases, now this is not the bottom ash. Imagine the ash that is affected here is the fly ash, because that is what was being captured by the baghouse or the ESP. That fly ash is now impacted with a number of sodium compounds, the sodium sulfates and bisulfates that have been created, as we saw in those chemical reactions. And so those ash, that changed ash may not be suitable depending on whatever the useful application that the untreated ash might have been previously used for. So you have to do an assessment. Of course, the facilities that are going to consider DSI, especially if they have ash sales, will definitely be looking at that and seeing whether that's still possible after this or whether it is not. We will come to in the next slide, a different concern on ash sales, which is if you don't sell the ash, you're landfilling it most likely or disposing it off, and that implication has to also be looked at. We'll get to that. And there is that the fly ash that is created with sodium compounds particularly has increased solubility for several metals, particularly things like arsenic and to a certain extent it's selenium and so on. So if you did have a standard process without the sodium compound injection, without Trona injection, or without sodium bicarbonate injection, and you are landfilling the ash, and you're landfilling it especially without any kind of leachate collection system or liner system, it was essentially a landfill that is either old or that is unlined for whatever reason, then you have to be extremely concerned about adding these sodium compounds and really significantly increasing the leachability of certain metal constituents in the ash. Research at this point shows that some compounds are not going to be leachable. You know, some of the heavier metals like lead and so on, they don't really seem to be affected. But arsenic in particular is extremely mobile, or at least in this form becomes extremely mobilized. And depending on how close you are to groundwater or how close you are to a receiving body like a river or a stream or wherever your landfill is located, that's a point of significant concern with DSI that I'd like to highlight here, and that may not be obvious to people who have thought of this purely as an air pollution control alternative to scrubbing or the more standard scrubbing, that this really has the potential of a water pollution problem down the road. You then have I mentioned CO2, I don't repeat it here again. Of course, CO2 formation is there with some other scrubbing systems, so it's not unique to DSI, but nonetheless, now that CO2 is a regulated pollutant, if you're putting in, you have to go through the new source review, depending on the size and so on. You may trigger DACT for greenhouse gases and go through that permitting process. I will not mention that because that's an obvious implication of increased CO2 emissions, even as a result of the control project for SO2. But then the other is you can get some increased NOx. You can form some additional NOx, and that has also not been fully quantified at this stage with a lot of hard data as to the extent of the NOx increase. Remember, this NOx increase is now likely to happen after an SCR or some such NOx control device, especially if the injection point is in the air preheater or after the air preheater, and it's not, upstream of the economizer. So you are going to create some NOx, and we have to. The evaluations for how much extra NOx will depend on the type of sorbent and the conditions under which it's being injected. So that is something else to keep in mind. Now, in some cases, to make things complicated, is you have actually seen some NOx reductions. Again, it depends on where it is injected and the temperature conditions. So whether NOx will form, whether NOx will, in other words, the NO component will reduce, the NO2 might go up. The issue of effect of NOx is an area that has not been fully evaluated. It can only be done on site-specific basis because of the variables involved in injection points and rates and so on. And then in some cases, this dry sorbent injection is likely to occur with other types of injection that are going on, like ACI with activated carbon injection for mercury control. You may be injecting, a facility may be injecting ACI, again, roughly in the same place, in order to capture that carbon ahead of their baghouse or their ESP. And so the cross-cutting aspect, the cross-sensitivity of both of these injections is something that has to be kept in mind. And some studies have shown a reduction in the ability of ACI to capture mercury when you simultaneously start adding Trona or adding DSI reagents into the same mix. Let's go to the next slide here. I think we're getting close to, so I had a few slides just showing that lots of people have tried lots of different reagents, and there are several operating ones in many companies right now that are based on Trona, based on lime. And like I said, the earlier installations were really focused on acid gases, and so they tend to be more calcium-based, like the lime shown on this chart. The newer ones are doing more focused on SO2, and therefore you have Trona. Let's go to another slide or two here, I think, with more lists of plants that are either evaluating or testing. Various vendors that have DSI have mobile platforms that they can bring to a facility and essentially do a longer term, maybe 6 to 8 week test and look at different parametric variations to try to find enough information so that they can do decent cost projections for capital and operating costs for these systems on a permanent basis. So we see a lot of that activity going on. I don't know if we have one more of this. I am trying to remember. Let's go to the next slide. Yep, this is another vendor. UCC is another vendor. And again, they have their customer list. I just took this off their website just to give folks an idea that there's a lot of activity. There is a lot of vendor activity as well as potential client activity. But I'm going to sort of reiterate that in addition to the CO2 increases, which are now captured by the permitting process, the impact on NOx, the cross impact on mercury, of course, have to be looked at from an air quality standpoint. And then to bring an even bigger concern is this impact on the changed nature of the ash, that is the fly ash, as a result of DSI, and its impact, longer-term impact on storage stability and potential leaching, especially if it is put in unlined landfills. That really has to be assessed and as part of an overall evaluation of this technology. I think that was the last one. Aaron, I don't know if we have any more. Let's go to, that's it. And so I know we have, I think, allowed for about 15, 20 minutes or thereabouts of questions. And just in case there are, we spill over, I can't get to all the questions, then if anybody wants to follow up, my contact information is provided on the screen. Thank you, everybody, for your attention. And now we can take questions.
Great. Thanks, Ron. We'll begin the question and answer part of the webinar now. Because DSI has so many particular different design implications and specific concerns, I'm going to focus on the questions that have a broader application, and then feel free to reach back out to Dr. Sahu to ask any particular questions that you might have happening in your region and with your coal plants. So for the first question, we have, what are typical temperatures at the air heater inlet and outlet?
The air heater inlet, I mean, most plants have a configuration where there's an economizer, and then there is, you know, there may even be a pollution control device like an SCR, and then there's an air heater. You might have temperatures in the, 400, 450. And keep in mind also that the temperature throughout, whether it's air heater inlet or outlet, will be a function of load. So, and when you, of course, design the injection system and so on, you're looking at not only full load operation, where you may get a certain type of a temperature, but you're also looking at part load or the cycling operation of the unit cycles, and you get to a lower load. You want to cover that full range of temperature variation at the air heater inlet. But it's not uncommon to get temperatures that are in the 400 or 500 degrees at the air heater inlet. But downstream of that, you might be down in the 375, 400 range. So those are rough numbers. You're not going to get 800 or 900 degrees at that point. Typically, after the air preheater, you're not capturing any more heat, so it's just going through a dust collector and then going up the stack.
Okay. The next question. What kind of questions and comments would you pose to permitting agencies regarding new permits for DSI in both landfill and air permits?
That's a really good question. That's really the heart of the presentation. Well, I would start with the obvious questions for the air permitting folks. The questions would be along the following lines. You have to have a good understanding of the entire injection system. So there may be fugitive emissions just as part of handling the sorbent as it comes into the facility. And how are those being properly addressed in the permitting process? You have multiple transfer points, you have silos. Now, typically they're enclosed because this reagent is not, it doesn't do well if it's just exposed. So you would expect that there would be fairly enclosed things just for operational reasons. Nonetheless, you have to make sure that there aren't any fugitive emissions or they're being properly calculated. There may even be small dust collectors in these silos I mentioned, that they're all being properly covered in the permitting process. You then have to look at the production of new pollutants like CO2. I mentioned CO2 is a byproduct if you use any type of Trona or sodium bisulfate. You may not get CO2 for certain reagents like hydrated lime, but you might get it for limestone. But focusing on Trona, you will definitely get CO2. So quantification of that, seeing whether it reaches a threshold for NSR for CO2, whether BACT analysis is required for that. That would be one line of questions. You then look at the impact of these other pollutants. I mentioned NOx and I mentioned mercury. In other words, the interaction of injecting Trona along with if other things are being injected like carbon, you want to look at the interaction, see if those emission rates of those pollutants are being affected, if they have been properly accounted for in the permitting process, especially if there are increases, likely increases in mercury emissions because of what you had previously intimated to the agency, and now you come in with a DSI system, and that might alter your mercury emissions. You might want to know about that. And then, of course, particulate emissions. Just like ACI, with this, you're adding a significant new load of particulates to your handling system. I mentioned, especially with the NSR ratios, hopefully you got the idea that these are significant additional loads, so they can be. If you're going to an NSR ratio of 2 or 3 or something in that range, you're adding a lot of new pounds of DSI. And how does your ESP handle that? In small quantities, ESPs actually do better with sodium, presence of sodium. They improve the efficiency. But if your sizing is not adequate, then you may not simply be able to handle, or you have to expand your air handling capability or your dust handling capability in your ESP or your bag house. Or your pressure drops might be too high, or your cleaning cycles might be affected, and therefore your maintenance and your reliability of the DSI along with the bag house and ESP might be affected. All of that will affect your particulate emissions, your potential, capability to have more malfunctions, and all those type of emissions or increased emissions have to be looked at. And then on your landfilling side, if you will, especially if you're going to have to increase the amount of dust you're landfilling, no question. These NSR ratios simply mean that you're going to have more dust, because a lot of it is simply the reagent that you just paid for, and now it has cycled through the system, and you're going to have to put it somewhere. And if your landfill is not lined, then leachability studies, the effect of increased leachability, not only on the new dust that you're bringing in, but also as you start adding this new sodium-based or sodium-impacted fly ash onto previous fly ash that might be in your pond. That's something that needs to be looked at. In other words, are you increasing the mobility of metals that are already in your landfill or in your impoundment or in your fly ash reservoir or wherever you have it as a result of putting new sodium-based higher leaching things? And what does it do to your arsenic, let's say, into your receiving waters, whether it's groundwater or surface waters? I would ask those questions. Anyway, again, just sort of walking through the whole train, those are some of the things that may be of interest.
Yeah, that was a very useful question. That was a question from John Blair. Our next question comes from Casey Roberts. If a DSI system is initially installed and designed to use with one sorbent, can it be later operated with a different sorbent? I think it's a question particularly asked hydrated lime to Trona.
Right. I was going to say that's a much harder switch. In other words, like going from a calcium base to a sodium base requires a lot more rejiggering of the air handling system, the capacities, and so on. And it has, because these reagents are very specific and unique, and in terms of their handling systems, in terms of how much you would need, and therefore the sizing may not be adequate to. It really depends, and maybe if the hydrated lime was designed to get 80%, but all you need is 40%, and can you do that? Of course you could, but as a general matter, I think it's harder to switch, hard to optimize. So let me put it this way: if you're willing to tolerate inefficiency, then switching is easier. If you're willing not to do that, but you'd rather have an optimized system, then I think it is a lot harder to just do a switch.
Okay. We have some more questions here. This is from Brad Van Gilder. When the system clogs due to unconditioned air, does it cause a failure of the bags and the bag houses, or what other failures may result?
Yeah, I was talking about the clogging and things are in the injection system. In other words, right from the storage silos in the blowers, you couldn't even inject it into the exhaust gases, or it becomes harder and harder to push the reagent into that injection system. That's where the clogging happens, because you're essentially forming cakes inside the pipes, and it's making it a narrower and narrower opening as time passes, and therefore your pressures start to really rise, and you cannot get the amount of Trona or so on that you want into the injection system. That's the difficulty. It's not so much a clogging, if you will, at the bag house. The impact on the bag house is simply a matter of you get more loading on your bags, you get more dust on your bags, you may have to clean them more frequently, and of course that has wear and other impacts on bag life. But there, it's not a clogging issue so much as a change in how you would operate your bag house in terms of the time it spends cleaning versus time it spends being cleaned, so to speak. That's the impact on the bag house.
Okay, and I'm going to combine two questions here, one from Deborah Payne and one from Christine Nianicelli, kind of get to the same issue. How old is this technology? Has it been tested sufficiently to prove effectiveness? And how long does it take usually to build and install a DSI system?
Well, the technology fundamentally has been around for a while, like I mentioned, over a decade. But in initial application, it was for other pollutants with much, much lower loadings, like removing some acid gases, removing SO3, which are really in far smaller quantities. They're present in smaller quantities. So this was used as a polishing system. You added a little sorbent to take care of very small quantities relative to SO2, very small quantities of HCl and SO3 that are present to remove sulfuric acid mist, to remove blue smoke, all kinds of things. And so in that form, the technology has been around for 10 to 15 years. The form it's being used right now, which is really as a primary control device for SO2, in lieu of, for example, a wet scrubber or even a dry scrubber, that is relatively new, and that is, let's say, I would say within the past 5 to 7 years. And initially, if you go to early literature, nobody even contemplated that this would be operated at plants that were sized at more than 300 megawatts, that this was going to be hard to do because of mixing and other problems. And of course, as we get more familiar, they're being proposed for much, much larger plants. And, the biggest plants we have in the country are 1,300 megawatt plants. I mean, they are the supercritical or plants of the Rockport class that we just saw the announcement from a few days ago. And there, you're not going to put all of this into one exhaust stream. Those plants are designed to have multiple exhaust streams. I think Rockport has 3 different parallel paths after the air preheater, or leading into the air preheater. So effectively, you have 3 400 megawatt or so units at each unit there. And now you're going to put DSI into those. Nonetheless, extremely large installations for handling the sorbents and the quantities that you need them. That scaling experience is new. We don't have a lot of experience with how that might function over the long term at those sizes. Having said that, there's no reason it shouldn't work if your goals are relatively modest and you learn the lessons of what have already been learned with regards to properly conditioning and handling and so on. The unknowns are, to me, the cross-media impacts. There really has not been a great deal of review or look, because it requires the water guys to pay attention to what's happening in the air world, or the waste guys to pay attention to what's happening in the air world as a matter of regulatory issues. And that's, I think, the big gap right now. Nobody has really focused on this additional leachability I mentioned and the downstream impacts to other water and other things. As to time, I think there was a question on schedule. You can get a system from design. It usually involves some pilot optimizations, so you're talking about a year, 18 months in that range to get a system from soup to nuts up and running. Compare that with about 3 to 5 years or so for a scrubber system, and you can see that this is a little quicker process to get up and running. I hope that answers the questions.
Great, thanks. We're going to wrap up with a couple more questions. We've had a lot of questions streaming in, so if they're not addressed on the webinar, I will forward them to Dr. Sahu, and he will try to respond in time. And also, to let you know, again, feel free to contact him with any specific questions after the webinar.
Yeah, I'd like to see if you guys can contact me. I'll try my best, but I wouldn't always know who answered what, and so if I'm tardy in getting back to you, please try to contact me if I can make that pitch.
Great. Yeah, thank you. And one question is, what is the parasitic energy use created by DSI?
Not a lot of hard data on that, because people have been playing with these conditioning systems and these blowing. So the parasitic loads are, obviously you have to blow the reagent into the injection point, and there the dehumidification, the cooling, the grinding, the pulverization, they all add to parasitic load. Very, very site specific. I don't have a lot of data on that I can generalize. The other end of parasitic is the impact on your baghouse and dust collection or ESP systems, especially if it's a baghouse and you have to have more pressure drops or more cleaning cycles. That is a form of parasitic load. Again, not a lot of publicly available or generalized information, and what is available, I'm aware of at least 2 or 3, but they're confidential studies done for particular situations that are not directly sort of transferable. But it's a great question, however, that it is. I would think it would be, just as a rule of thumb, something in the in the order of magnitude of a dry scrubber, but probably not as much as a wet scrubber.
Okay, great. And one more question before we wrap it up. What would be the typical ratio of CO2 emissions as percentage of total CO2 when treating moderate to high sulfur coal emissions with sodium DSI?
I have to do the math. I don't have the number offhand. Yeah, if I understand the question, it is, in other words, how much incremental CO2 would this create in addition to the CO2 that is coming out of the combustion system? A key input into that would be the sulfur dioxide reduction expected, or the sulfur dioxide rate of the unit. You really couldn't, there's no number without, in other words, you want to know how much SO2 is actually going to be required to be removed, because that will dictate how much CO2 you're going to produce. But that's a relatively straightforward calculation once you have that number and can be done.
Okay, great. Well, I guess at this time we'll end the question and answering session. Thank you all for attending and asking the questions. I think it's a very important subject for all of us to think further about. Also, SACE has commissioned Dr. Sahu to write a report on DSI as a pollution control technology, both generally and as implemented at southeastern coal plants. We plan to finalize this report within the coming weeks, and we'll reach out to each of you on this webinar to let you know when that report is publicly available on our website.
Thank you, everybody. Thank you for your attention.
Okay. Bye.
Okay, great. Thank you. Thank you, Dr. Sahu. Thank you, Angela. We are really excited about our monthly webinar series, and we hope you'll join us again. Please visit our website, cleanenergy.org, for more information. And as I mentioned earlier, the presentation and the recording of today's webinar will be posted on our website via our webinar archive page, and you will receive a link to that presentation as well. Okay, thanks everyone, and have a great rest of your day.
Bye-bye.